Hello, my name is Professor Niazi. Today, we're going to be talking about part 2, how to derive the sine and cosine values at the special angles. In the first video, we discussed how to find all the special angles using the 30-15-15 rule. The 30-15-15-30 rule. However, we did not discuss what the cosine and sine values were at those points. I'm going to show you how to derive those points. After that, you will no longer need to memorize, but you will understand why the sine and the cosine values are those values. Now, to begin, we have a unit circle. Notice that this is our x-axis and this is our y-axis. Now, we'll start at a special angle, 45 degrees, also known as in radians, pi over 4. This is why trigonometry sounds like you're studying triangles. Trigonometry. It sounds like you're studying triangles. And although trigonometry is all about various aspects of the triangle, you will now see that triangles are just mere tools that us mathematicians utilize in order to understand the properties of the circle. We utilize triangles to parameterize how the x component and the y component of a circle changes. Let me elaborate on what I mean by that. After we draw out this line, and we know it's a unit circle, so its length is 1, that 1 length here ends up becoming the hypotenuse of a right triangle when I draw a straight line down to the x-axis. This value being the x value, this value being the y value, and here the hypotenuse is equal to 1. With this being pi over 4, the same thing as 45 degrees. Now, let's cut out that value. Let's just redraw this situation here. This is pi over 4, also known as 45 degrees. Okay? Now, we have a hypotenuse that is of length 1. And we have some x and we have some y. We don't know what that is yet. We are going to make this assumption. It's a very good assumption. That in fact the value of x is equal to the value of y. How are we assuming this? Where am I coming up with this stuff? Well, think about it like this. If you remember the other special angles, let me get a distinct color here. The other special angle was an angle less than pi over 4, actually right here at pi over 6. And furthermore, there was another special angle more than pi over 4 over here at pi over 3. Notice now that when I play the same game and bring down, also known as project, this value down here onto the x-axis, notice that this leg length in the blue and over here in the green as you can see right here, this middle is the black. Okay. Take a look here. At pi over 6, the x value, which is the value on the x-axis, it's longer than at pi over 4. Furthermore, at pi over 3, the x-axis is shorter than at pi over 4. Can you see that? It makes complete sense. The x value is shorter at that more steep angle whenever we bring it down, because it's just higher up here on the circle. Whenever we bring it down, there's less x. And over here, same thing. In the middle, it's over here, but whenever you do a more shallow angle, it lands here on the circle and it falls farther than the black line. The blue line falls farther than the black line. It is this very fact that allows us to assume that at halfway point, which is 45 degrees, whenever you cut 90 degrees, this first quadrant, there's a total of 90 degrees here. Whenever you cut the 90 degrees in half at 45 degrees, we get pi over 4. And that is exactly when the x length and the y length will be the same. Notice that here, although the x length is the largest out of the three in the blue, the y length is the shortest. Over here, although the green x length is the shortest out of the three colors here, the y length is the longest for pi over 3. So we can agree now, pictorially at least, this is not a rigorous mathematical proof, but it's sufficient for this video and for this audience, that we can now actually assume that x is equal to y at 45 degrees, meaning this leg length and this leg length are the same at this very point. If you still have any questions about that argument, please put it in the comments and send me an email. I'd love to answer and discuss it with you back at home. So, upon justifying this assumption, we can now derive what the sine and the cosine values are at this very point. Recall that the sine of angle theta is really the opposite leg of the triangle divided by the hypotenuse. So over here, the sine of pi over 4 is going to be the opposite leg, the y, over the hypotenuse. And the hypotenuse is really 1, so it's y over 1, which is just y. This is why we say that the sine value parametrizes the y. Because really, it parametrizes how long this leg is. By parametrize, that's just a fancy word for measurement. And the cosine of some theta, here our theta in particular is pi over 4, is really the adjacent leg over the hypotenuse. And in this case, take a look. Cosine of pi over 4 is equal to x over the hypotenuse, because this is the adjacent to pi over 4, and this was the opposite to pi over 4. That's really x over 1, which is just x. So we can see that cosine parametrizes the x, and the sine parametrizes the y. Now, let us discuss this assumption up here in the frame of reference of the Pythagorean theorem. When we utilize the Pythagorean theorem to this situation, hypotenuse squared is equal to x squared plus y squared. We know the hypotenuse is really 1, and 1 squared is 1. Furthermore, we can change this y to an x because of our assumption. So this is x squared plus x squared. And we could have turned x to a y. Doesn't matter. We decided to go with x. Mathematicians love x. And so 1 is now equal to 2x squared. Now I solve for x. I divide both sides by 2. I'll bring this calculation up here. Divide both sides by 2. So I get 1/2 is equal to x squared. Then I take the square root of both sides. And I get x is equal to the square root of 1/2. From pre-calc 1, you know, or college algebra, that the square root distributes across multiplication and addition. Multiplication and division. And so it goes to the numerator and the denominator. Square root of 1 is 1. And I get square root of 2 in the denominator. Once I rationalize the denominator, multiplying top and bottom by a fancy number 1, I get root 2 over 2 as the value for x. But that's also the value for y, because we assumed that they're the same, recall. Now, I know what you're thinking. You're throwing tomatoes at me at home. You're eating the tomato, and now you're chugging it at your screen because you're saying you are taking an even root, a square root. You should be saying plus or minus root 2 over 2. And you are correct. There should be a plus or minus here in terms of algebra. However, in terms of the geometrical location, we only take the positive. Why is that? Well, in the first quadrant, the cosine values, which are parameterizing the x, they're positive. And the y values, which are parameterized by the sine, they're positive. And so negative square root of 2 over 2 would imply something in the third quadrant if they're both negative, meaning both x is negative and both y is negative. Okay? So we only say positive in order to respect the fact that it's here in the first quadrant. Good. Now you can save those tomatoes and eat them. They're filled with nutrients to make you grow big and strong. Now, we have discussed that cosine, which is x, is root 2 over 2, and sine, which is y, is root 2 over 2. So I can actually say that the cosine, which is the x, is root 2 over 2 here, and the sine is root 2 over 2 here. We've derived those values. Next, I'm going to derive the value for pi over 6 and pi over 3. You'll notice very soon that upon doing this derivation, that doing one solves the other. Now, let's do a triangle in which this is at pi over 6. This is the right degree. And notice pi over 6 is really 30 degrees, meaning that up there, this is going to be 60 degrees. Okay? And over here, this will be our x again, and this will be our y. And we are living on a unit circle. We require this to be 1. However, in the proof for the values of the cosine and sine, the x and the y, I'm going to create a different triangle. A different one than this. I'm going to have to create a larger triangle. And you'll see why I do that. The fact that we can create larger triangles and rescale them back to shorter triangles, like this, I want a triangle with hypotenuse 2 instead of 1. With an x, if we're at pi over 6 here, I want the x to be square root of 3 and the y to be 1. Why am I doing this? Why can I create a triangle with these values? Well, because it satisfies the Pythagorean Theorem that the two legs values squared are equivalent to the hypotenuse value squared, because 4 is equivalent to 3 plus 1. That means this is an actual bona fide triangle. You can actually create a triangle with these various leg lengths. Why these? Why am I picking these values? That's a great question, and I know you're wondering it. I'm going to answer that. This is due to the fact that the Pythagorean Theorem allows us to scale triangles. For a triangle with a C, A, and B right here, with some angle theta, I can scale this triangle as long as it retains c squared is equal to a squared plus b squared. I can multiply both sides by some type of proportionality constant, call it m. That means mc squared is equal to ma squared plus mb squared. This is a valid expression in which we've scaled the triangle by m. I'm going to choose my m to be 1/4. Why is that? Well, I picked 1/4 because that is the square of a half. And a half is what I need to multiply this hypotenuse by in order to make it 1, to restore it to a viable triangle that will fit inside the unit circle. Okay? You'll see what I mean in a second here. Notice that over here, this forms a triangle, correct? Okay. So then these leg lengths here work. So I'm going to scale it by 1/4. Take those values and scale it by 1/4. So my c squared is equal to a squared plus b squared times my m. Let m be equal to 1/4. Because really any number works. Even 0. You would just get something that's not even a triangle at all. It'll be 0 is equal to 0. It'll just be a point. It won't be anything. So we'll scale this by m, which is 1/4. So over here, we'll get 1/4 times our leg lengths over there. 2 squared, which is equal to square root of 3 squared plus our 1 squared. Okay? Then we'll get 1/4 times all that, so it's 1/4 times 4. That's equal to 1/4 times 3 times 3 plus 1/4 times 1. As you can see here, things reduce down to becoming 1 is equal to 3/4 plus 1/4. So we can scale. We can scale. And we could have scaled afterwards by 1/4, or we could have scaled prior by a half. What do I mean by that? Well, I mean that I could say 1/2 times 2, square that, is equal to cube root of 3 over 2 squared plus 1/2 squared. Really, this is 1/2 times 1. And really, this is 1/2 times root 3. Notice that that reduces to 1 squared is equal to root 3 over 2 squared plus 1/2 squared, which is exactly what we have over here. This reduces to 2 over 2 squared, which is just 1, is equal to root 3 over 2 squared plus 1/2 squared. And 2 over 2 is really 1. So it reduces to a triangle that has hypotenuse 1, x value root 3 over 2, and y value 1/2. So this is just the difference between squaring and then scaling, or scaling and then squaring. This is the reason why at the pi over 6, the cosine value is root 3 over 2, and the sine value is 1/2. You won't need to know this stuff for a test unless you're taking higher level mathematics that requires proofs and whatnot. But I would like to explain to those in class, the individuals that I don't teach, all of you out there at home, I'd like to explain to you the reasons for these things, because I believe mathematics becomes so much more rich, beautiful, and unlimited whenever you understand that these values don't come out of thin air, that there's reasons for them, and that you are actually capable of understanding those reasons. These arguments are not so crazy that you will be over your head. They just require a little bit of clarification and an explanation. And now, not only do you know that the cosine is root 3 over 2 and the sine is 1/2 over here, you don't memorize that. You just understand it. You understand that it's just an application of the Pythagorean Theorem. And it's just whatever you do to one side, you do to the other. You can multiply both sides of the Pythagorean Theorem by 1/4. And it will scale your triangle to the appropriate hypotenuse. Because remember, this triangle won't fit inside the unit circle. It will go past the unit circle because it has hypotenuse 2. This triangle, though, fits beautifully inside of our unit circle, and it reveals to us what the cosine and the sine values are at pi over 6. All that work, and now we got to do it for pi over 3, but it's not that hard because you just change your frame of reference. Notice that 60 degrees over here is pi over 3. So we can just say sine and cosine, but looking at it from a different perspective. Here to pi over 6, the adjacent is root 3 over 2. But over here at 60 degrees, also known as pi over 3, the adjacent is 1/2. So I'll erase this 60 degrees and call it pi over 3. Whenever we're looking at things in terms of this angle, this leg becomes the adjacent, and this leg becomes the opposite. Whereas when we look at the trigonometric functions via this frame of reference, at pi over 6. X is the adjacent and y is the opposite. So they flip. Because they flip, they also, the numerical values flip here. Why? Well, because the cosine of pi over 3 is now adjacent, which is 1/2, all over hypotenuse, which is 1. That equals 1/2. That's where this comes from. And furthermore, the sine of pi over 3 becomes opposite root 2 all over hypotenuse, which is 1, which is just root 3 over 2, and that's where this comes from. Isn't that cool? Isn't math cool? Yeah! So, what about right here? And what about right here? Well, those are very easy questions to answer. At this point, you have all x, no y. So 1, 0 for x and y component. And over here, you have all y, no x. So 0, 1 here. Now I'm telling you, the hard part was just establishing these results here in the first quadrant. After you have these results, the rest are easy. Easy peasy lemon squeezy for sheezy. And I'll show you. We'll just put this right here. These are the various special angles. If you watch the first video, you know what those values are and how to derive them. We will skip that part and just designate these special angles with these lines. I must delete this x here. Put it right there. So this is at pi over 2. This is at 2 pi over 3. Yada yada yada. You know the 30, 15, 15, 30 rule that I taught you in the first video. Apply that rule. Add 30, 15, 15, 30 to the various angles recursively, and you'll be able to derive all of these angles. So that's not the part that I want to talk about today. Today I want to talk about, in this video, what is the cosine and sine values at those parts. And we will be doing that here. I'm going to clear up some real estate here. Over here, at the next special angle, notice that x values go beyond to the left of the origin. And so that means they become negative. However, numerically, they're going to be the same as this counterpart right here. So this just becomes a negative 1/2, and the y is at the same height, the x is at the same length, it's just in the opposite direction, so this retains this root 3 over 2. Over here at this next special angle, it's very much like its 45-degree analog. It's going to have these same values. However, the x is going to be, you guessed it, negative, because it's opening to the left. Alright? Down here, it's going to be very much like this pi over 6 analog. However, the x values are, you guessed it, negative. Negative cube root 2, negative square, negative root 3 over 2, all in 1/2. Okay? How about right here? You guessed it, it's going to be like this, except the x will be negative. Are you seeing the pattern? I know you're seeing a pattern. And if you don't see it, wait until the end of the video. If you don't see it at the end of the video, watch it again. Don't ever give up. You can achieve anything. No matter how difficult this may seem to you, you are capable of understanding it. Mathematics was invented by human beings. And last time I checked, you're a human being. Let's keep going. Over here, we have more values. This is going to be analogous to this right here. Its counterpart, right across it. Go across the bridge and you'll see its counterpart. And it's at pi over 6. However, what is the cosine and what is the sine? Notice they're both negative because this is to the left of the x and it's actually to the below of the origin. So down here is negative y. To the left here is negative x. And notice we have negative x and negative y in the third quadrant. So this is quadrant 2, this is quadrant 3, quadrant 4, quadrant 1,